Welcome to Tech with Kaushik. This is set 2 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 2. Question number 21. We're working with deployment strategies here. Consider this situation. A development team is migrating a Java application running on Apache Tomcat to AWS Code Deploy. The application will be deployed across multiple environments: development, staging, and production. The logging verbosity for the application is defined in a configuration file on the server. The team wants the log level to automatically adjust based on the target environment, for example, debug in development, warn in production. They must accomplish this using a single universal application revision artifact for all environments to ensure consistency. How can the DevOps engineer meet these requirements with the least operational overhead? Review the options. Option A. Add an AWS CLI command in the code deploy after install lifecycle script that queries the EC2 instance metadata, maps the instance ID to the corresponding environment, and rewrites the log configuration file. Option B. Utilize the implicitly available deployment_group_name environment variable within a script executed during the code deploy before install lifecycle hook to determine the environment and modify the log configuration file accordingly. Option C. Define custom parameters in AWS Systems Manager parameter store. Add a script to the validate service lifecycle hook that fetches the parameters based on the instance tag and restarts the service. Option D. Create a different code deploy appspec.yml file for each environment. Configure code pipeline to inject the correct appspec.yml file into the artifact during the build stage. The best choice is option B. Utilize the implicitly available deployment_group_name environment variable within a script executed during the code deploy before install lifecycle hook to determine the environment and modify the log configuration file accordingly. Here's why. AWS Code Deploy injects several built-in environment variables into the context of the executing deployment scripts, including deployment_group_name and deployment_group_ID. Because the deployment groups typically map to environments, for example, dev deployment group, prod deployment group, a bash or PowerShell script in the before install or after install hook can read this variable and perform a quick string replacement to set the appropriate log level without requiring separate application revisions. Let's quickly check the incorrect choices. A. Querying the EC2 instance metadata requires custom IAM roles, parsing tags, and additional latency. The code deploy environment variables provide this context natively and instantly. C. While parameter store is valid for configuration management, requiring an external API call when the deployment group name is already natively available locally in the environment variables adds unnecessary overhead. D. Managing multiple appspec.yml files and repackaging the artifact based on the environment violates the principle of promoting an immutable release artifact through the pipeline. A helpful shortcut is this. AWS Code Deploy passes standard environment variables, like deployment_group_name, into its lifecycle hooks. Use them to write environment-aware scripts without modifying the source artifact. Here comes question number 22. A development team uses AWS Code Commit for version control and AWS Code Build for continuous integration. Developers want every pull request creation and source branch update to automatically run long-running integration tests before reviewers decide whether to merge. The final pass or fail result must be visible directly on the pull request. Which solution will achieve this requirement? Here are the options. Choice A. Create an Amazon EventBridge rule for code commit pull request creation and source branch update events that invokes a Lambda function to start code build. Create a second EventBridge rule for code build state changes that invokes Lambda to post the specific build result and result link as a comment on the code commit pull request. Choice B. Configure an AWS code pipeline to monitor all branches. When a branch is updated, trigger a code build project. Configure code build to send SNS notifications to the PR author upon failure. Choice C. Create an Amazon EventBridge rule that reacts to pull request status changed. Trigger a code build project directly to run tests. Configure the code build project to update the code commit repository commit status. Choice D. Create an AWS CloudTrail rule that monitors for Git pull events. Trigger an AWS step function state machine to run code build tests and merge the code automatically if the tests pass. The right response is option A. Create an Amazon Event Bridge rule for code commit pull request creation and source branch update events that invokes a Lambda function to start code build. Create a second Event Bridge rule for code build state changes that invokes Lambda to post the specific build result and result link as a comment on the code commit pull request. The main reason is code commit emits pull request state change events to Event Bridge, so PR creation and source updates can start code build automatically. Code build state events can then trigger a Lambda function that calls the code commit comment API to place the completed pass or fail result on the same pull request. This gives reviewers per PR test visibility without polling. Now let's rule out the other options. B. Branch-triggered code pipeline plus SN South does not place the test result on the pull request. C. A pull request status change is not the correct trigger for every source update, and code build does not natively update a generic code commit status field as described. D. Git pull is not a reliable PR creation trigger, and automatically merging removes the requested reviewer decision. Use code commit PR events to start tests and code build state change events to publish completed results back to the PR through the code commit API. Question number 23. Scenario. A company uses AWS code pipeline for its release process. The final stage deploys a compiled Java application packaged as a JR file to a fleet of Amazon EC2 instances managed by an auto-scaling group. The pipeline previously used a custom AWS code build script to handle deployments over SSH, but the company now wants to use AWS code deploy to orchestrate the deployment natively. The EC2 instances are launched from a custom hardened AMI. Which combination of steps is required to transition the pipeline to use AWS code deploy? Choose 2. Choose every option that satisfies the requirement. Option A. Bake the AWS code deploy agent into the custom AMI. Ensure the EC2 instances are launched with an IAM instance profile that allows the agent to communicate with code deploy. Option B. Include an appspec.yml file in the root directory of the application source code to define the deployment lifecycle hooks and file mappings. Option C. Add an EC2 image builder stage to the code pipeline to generate a new AMI on every commit and configure code deploy to perform an immutable deployment. Option D. Configure the code build project to install the code deploy agent onto the target EC2 instances dynamically during the build stage using systems manager run command. E. Update the EC2 auto-scaling group launch template to execute the code deploy deployment directly via a user data script. The answers that work here are option A. Bake the AWS code deploy agent into the custom AMI. Ensure the EC2 instances are launched with an IAM instance profile that allows the agent to communicate with code deploy. And option B. Include an appspec.yml file in the root directory of the application source code to define the deployment lifecycle hooks and file mappings. To use AWS code deploy to deploy applications to Amazon EC2 instances, the EC2 instances must be running the AWS code deploy agent, and they must have an IAM instance profile attached with permissions to pull the code deploy service. A. The application artifact being deployed must contain an appspec.yml file in its root directory. Code deploy uses this file to determine which files to copy to the instances and which lifecycle scripts to execute. B. The other choices do not work because C. EC2 image builder creates AMIs, which implies immutable infrastructure, replacing the instances completely. Code deploy can perform in-place deployments to existing instances, so generating a new AMI on every commit is unnecessary overhead unless explicitly adopting an immutable AMI pipeline. D. While Systems Manager can install the agent dynamically, baking it into the custom AMI ensures the agent is consistently ready before code deploy attempts to connect, minimizing race conditions during scaling. E. Code deploy deployments are triggered via the code deploy service or code pipeline, not by calling code deploy from the EC2 user data script. Exam tip. AWS code deploy on EC2 requires 3 core things: the code deploy agent running on the instance, an IAM instance profile allowing access, and an appspec.yml file in the application revision. Now for question number 24. Next, Let's move into artifact management. Here's what is happening. During a security audit, it was discovered that an AWS code build project is downloading a proprietary database seed script from an Amazon S3 bucket using public, unauthenticated HTTP requests. The S3 bucket currently has an open bucket policy allowing public read access. The security team requires that all unauthenticated access to the S3 bucket be revoked immediately, but the code build project must still be able to retrieve the script securely during the build phase. How should a DevOps engineer correct this issue securely? Choice A. Modify the S3 bucket policy to deny public access. Create a dedicated IAM user, generate access keys, and hardcode the keys in the code build spec.yml to authenticate the S3 download command. Choice B. Enable S3 pre-signed URLs on the bucket. Configure a pre-build hook in code build to dynamically generate a URL and use curl to download the file. Choice C. Modify the S3 bucket policy to deny public access. Update the IAM service role attached to the code build project to include S3. Get object permissions for the bucket. Update the build spec.yml to use the AWS S3 command to download the file. Choice D. Update the code build project settings to include the S3 bucket in the allowed buckets configuration. Keep the bucket policy unchanged, but enable AWS KMS encryption on the file. Go with option C. Modify the S3 bucket policy to deny public access. Update the IAM service role attached to the code build project to include S3. Get object permissions for the bucket. Update the build spec.yml to use the AWS S3 command to download the file. This works because the most secure and native way to allow an AWS service to access private Amazon S3 objects is to use IAM roles. AWS code build runs using an associated IAM service role. By granting this service role S3, get object permissions to the specific S3 bucket. Code build can securely authenticate to S3 using temporary credentials automatically provided to the AWS CLI environment during the build. Here's why the alternatives are not suitable. A. Hardcoding static IAM access keys in source code or build scripts is a major security vulnerability and violates best practices for secret management. B. Generating pre-signed URLs dynamically adds unnecessary complexity compared to native IAM role authentication. D. Allowed buckets is not a valid code build project setting for bypassing S3 bucket policies. Code build authorization is handled entirely via its IAM service role. Here's a useful exam tip. Avoid hard-coding credentials or generating pre-signed URLs when AWS services need to talk to each other. Use the native IAM service role attached to the calling service, like code build, EC2, or Lambda, to grant access. Next, question number 25. An e-commerce order processing system relies on an Amazon Simple Queue service, Amazon SQS, queue, and an AWS Lambda function. The Lambda function is configured with reserved concurrency to process messages from the queue and write the parsed order data into an Amazon DynamoDB table. The DynamoDB table uses provision capacity with auto-scaling enabled for both reads and writes. During high-volume sales events, users report that their order status is severely delayed. A DevOps engineer investigates and suspects that the processing pipeline is bottlenecked. Which combination of actions should the DevOps engineer take to identify and resolve the delays? Choose 2. Select all answers that apply. Options. Option A. Review the approximate age of oldest message metric for the SQS queue. If it is high, increase the reserved concurrency limit of the Lambda function to allow more concurrent processing. Option B. Review the number of messages sent metric for the SQS queue. If it is spiking, increase the visibility timeout of the SQS queue to prevent duplicate processing. Option C. Review the write throttle events metric for the DynamoDB table. If throttles are occurring, increase the maximum write capacity units, WCUs, on the table's auto-scaling policy. Option D. Review the throttles metric for the Lambda function. If throttles are occurring, increase the Lambda function execution timeout parameter. Option E. Review the system errors metric for the DynamoDB table. If errors are occurring, configure an SQS dead letter queue, DLQ, with a redrive policy. You should choose option A. Review the approximate age of oldest message metric for the SQS queue. If it is high, Increase the reserved concurrency limit of the Lambda function to allow more concurrent processing. And option C. Review the write throttle events metric for the DynamoDB table. If throttles are occurring, increase the maximum write capacity units, WCUs, on the table's auto-scaling policy. Let's look at the reasoning. A delay in processing means a bottleneck exists in the pipeline. The approximate age of oldest message metric indicates if messages are sitting in the SQS queue for too long. If this is high, the Lambda function is not processing messages fast enough. Increasing the reserved concurrency allows more Lambda functions to spin up and drain the queue faster. Because DynamoDB is receiving the final output, write throttling can cause the Lambda function to retry or stall. The write throttle events metric indicates if DynamoDB auto-scaling is hitting its configured upper boundary. If so, increasing the maximum WCU limit will allow the table to scale up further and absorb the burst. C. The remaining options can be eliminated because B. Number of messages sent measures producers adding to the queue, not consumers. Increasing the visibility timeout does not speed up processing. It just prevents messages from reappearing while being processed. D. Throttles on a Lambda function indicate that the invocation limit is reached, concurrency bottleneck, but increasing the timeout only lets a single execution run longer. It does not increase concurrency. E. While DLQs are good for poison pill messages, standard scaling bottlenecks cause latency, age of message, or throttle events, not necessarily unhandled system errors. Keep this point in mind for the exam. When troubleshooting serverless pipelines, SQS leads to Lambda leads to DynamoDB. Check approximate age of oldest message for queue backlog, Lambda concurrent executions, or throttles for compute bottlenecks, and DynamoDB provision write capacity units / write throttle events for storage bottlenecks. Next up is question number 26. We're moving on to auto remediation. Here's the scenario. A company operates hundreds of Amazon EC2 instances within a single AWS region. Instances are frequently launched and terminated by various developer teams. A new corporate security policy mandates that every running EC2 instance must have an IAM instance profile attached. If an instance is launched without an instance profile, it must automatically be assigned a specific default instance profile that contains no permissions. The solution must enforce this for all existing instances and any instances launched in the future. Which solution will satisfy this requirement with the least operational overhead? The choices are: Option A, create an Amazon Event Bridge rule triggering on run instances API calls via AWS CloudTrail. Configure the rule to invoke an AWS Lambda function that attaches the default profile to the new instances. Option B, enable the AWS config managed rule EC2 instance profile attached. Configure an automatic remediation action that triggers an AWS Systems Manager automation runbook to attach the default instance profile to non-compliant instances. Option C, create an IAM permissions boundary that denies the EC2 run instances action unless the IAM pass role condition is met. Attach the permissions boundary to all developer IAM roles. Option D, configure an AWS config custom rule that runs on a nightly schedule to evaluate all EC2 instances. Route non-compliant results to an Amazon SNS topic for manual remediation. In this case, choose option B. Enable the AWS config managed rule EC2 instance profile attached. Configure an automatic remediation action that triggers an AWS Systems Manager automation runbook to attach the default instance profile to non-compliant instances. This is the best choice because AWS config is the optimal service for continuously evaluating resource configuration compliance. The managed rule EC2 instance profile attached natively detects any EC2 instances missing an IAM instance profile. By configuring an automated remediation action utilizing Systems Manager automation, AWS will automatically attach the default profile whenever a non-compliant instance is detected, covering both existing instances and any newly launched ones. Event Bridge acting on run instances only captures instances at launch time. It will not remediate existing instances already running without a profile. C. A permissions boundary limits what an IAM role can do. It cannot force a developer to attach a specific instance profile or attach one automatically. D. A custom AWS config rule requires custom Lambda code to maintain, and SNS notifications require manual intervention, violating the requirement for low operational overhead and automated enforcement. The main takeaway is for requirements involving retroactive compliance, evaluating existing resources, combined with future enforcement. AWS config paired with Systems Manager auto-remediation is the standard AWS best practice. Now for question number 27. Here's the scenario. A DevOps engineer is configuring a continuous deployment pipeline for a critical serverless application built using the AWS Serverless Application Model, AWS SAM. To protect users from bugs introduced during deployments, the business requires a deployment strategy that safely shifts a small percentage of traffic to the new AWS Lambda function version for a short period. If error rates increase during this period, the deployment must automatically roll back without manual intervention. Which configuration will meet these requirements natively? Review the options. Choice A. Use AWS SAM with the auto publish alias property. Define a deployment preference type of canary 10% 15 minutes and configure alarms referencing Amazon CloudWatch error metrics for the Lambda function. Choice B. Define two AWS CloudFormation templates. Deploy the new template alongside the old one. Use an Amazon Route 53 weighted routing policy to shift 10% of traffic, and use Route 53 health checks to roll back. Choice C. Configure an AWS code pipeline manual approval stage. Deploy the Lambda function to 10% of instances. Wait for the developer to approve the CloudWatch metrics, and then proceed with the remaining 90%. Choice D. Update the Lambda function's environment variables to include a feature flag. Use AWS app config to slowly ramp the feature flag to 10% of users over 15 minutes. The answer here is option A. Use AWS SAM with the auto publish alias property. Define a deployment preference type of canary 10% 15 minutes and configure alarms referencing Amazon CloudWatch error metrics for the Lambda function. Here's why. AWS Serverless Application Model, AWS SAM, natively integrates with AWS Code Deploy to perform safe, automated deployments for AWS Lambda. By specifying the auto publish alias and a deployment preference like canary 10% 15 minutes, Code Deploy orchestrates traffic shifting. Specifying alarms ties CloudWatch metrics to the deployment. If the alarms breach, for example, error rates spike on the new version, Code Deploy automatically halts the deployment and rolls back the traffic to the previous version. Let's quickly check the incorrect choices. B. Using Route 53 to shift traffic for Lambda functions requires placing them behind an API gateway and using custom domains, which is much more operationally complex than native SAM/Code Deploy integrations. C. Manual approval stages in code pipeline require human intervention, violating the requirement for automatic rollback. D. Feature flags via app config shift application-level logic for users, but they do not manage the actual underlying Lambda deployment or provide the native automatic infrastructure rollback capabilities of SAM and Code Deploy. A helpful shortcut is this. To implement canary or linear deployments natively for AWS Lambda with automatic rollbacks based on metrics, use AWS SAM with the deployment preference and alarms properties. Question number 28. Let's go. The focus now shifts to infrastructure as code. Scenario. An application is provisioned automatically via an Amazon EC2 user data script that downloads software artifacts from an external repository upon instance launch. Previously, the EC2 instances were launched in a public subnet with auto-assigned public IP addresses. Due to updated security standards, the DevOps team must now launch these EC2 instances in a private subnet with no inbound or outbound internet access permitted. Following this network change, the instances launch and pass their health checks, but the user data script fails to download the software artifacts. What is the most secure way to ensure the application artifacts are installed while strictly complying with the No Internet policy? Choices. Option A. Deploy a NAT gateway in a public subnet and update the private subnet's route table to point 0.0.0/0 to the NAT gateway. Option B. Temporarily attach an elastic IP address to the instances during launch. Run a Lambda function via Event Bridge to disassociate the EIP once the installation script completes. Option C. Upload the application artifacts to an Amazon S3 bucket. Create a VPC gateway endpoint for Amazon S3 in the VPC. Assign an IAM instance profile to the EC2 instances granting read access to the S3 bucket. Option D. Create an AWS Transit gateway and route the private subnet traffic to an isolated on-premises artifact repository. The answer here is option C. Upload the application artifacts to an Amazon S3 bucket. Create a VPC gateway endpoint for Amazon S3 in the VPC. Assign an IAM instance profile to the EC2 instances granting read access to the S3 bucket. The main reason is a VPC gateway endpoint for Amazon S3 allows resources within a private subnet to access S3 over the AWS private network without requiring an internet gateway, NAT gateway, or public IP addresses. This perfectly satisfies the strict security requirement of having no inbound or outbound internet access. The EC2 instance profile securely provides the necessary credentials for the user data script to authenticate and download the artifacts using the AWS CLI. Now let's rule out the other options. A. Deploying a NAT gateway violates the strict requirement that instances have no outbound internet access permitted, as a NAT gateway provides general internet access. B. Attaching an elastic IP requires an internet gateway and a public route, which violates the security policy. D. Routing traffic to an on-premises repository via transit gateway is excessively complex, expensive, and unnecessary when AWS natively provides VPC endpoints to access S3 privately. When EC2 instances in an isolated private subnet, no NAT or IGW, need to download artifacts or logs, place the files in Amazon S3, and configure an S3 VPC gateway endpoint. Next up is question number 29. Consider this situation. A DevOps team uses AWS CodeCommit to host their source code and AWS Code Pipeline to orchestrate their CI/CD deployments. The pipeline is configured to automatically trigger whenever code is pushed to the main branch. A developer recently pushed several new commits to the main branch, but they report that the pipeline did not execute. The developer waited 15 minutes, but the pipeline execution history shows no recent activity. What should the DevOps engineer check first to troubleshoot why the pipeline failed to trigger? Here are the options. Option A. Verify that an Amazon Event Bridge rule exists and is enabled to capture code commit repository state changes and trigger the pipeline. Option B. Check the IAM permissions of the developer to ensure they have the code pipeline. Start pipeline execution permission. Option C. Inspect the code build spec file to ensure there are no syntax errors preventing the build stage from starting. Option D. Review AWS CloudTrail to verify if the code pipeline service role has permissions to assume the code commit repository read role. The best choice is option A. Verify that an Amazon Event Bridge rule exists and is enabled to capture code commit repository state changes and trigger the pipeline. By default, AWS Code Pipeline relies on Amazon Event Bridge rules to detect changes in an AWS code commit repository and trigger pipeline executions automatically. If the pipeline is not starting when new commits are pushed, the most common architectural reason is that the Event Bridge rule was accidentally deleted, disabled, or misconfigured. The other choices do not work because B. Developers push code to code commit using Git permissions. The pipeline itself runs automatically via Event Bridge. The developer does not need the start pipeline execution permission unless triggering it manually via the AWS console or CLI. C. A syntax error in the code build spec.yml would cause the pipeline to fail during the build stage. In this scenario, the pipeline execution history shows it didn't even start. D. While IAM roles are important, code pipeline failure to start on push is primarily governed by the Event Bridge trigger mechanism. If the role was wrong, the pipeline would start but immediately fail with an access denied error. Exam tip. Code pipeline uses Amazon Event Bridge, formerly CloudWatch events, under the hood to automatically trigger executions based on source repository changes, code commit, S3, or GitHub via webhooks. Question number 30. This question takes us into event-driven automation. A company provides Amazon EC2 instances to developers as remote workstations. The security team mandates that no EC2 security group can have inbound rules allowing unrestricted access 0.0.0/0 on port 22 or 3389. A DevOps engineer has written an AWS Lambda function that parses security group IDs from an event payload, removes any unrestricted inbound rules, and publishes a notification to an Amazon SNS topic. The engineer now needs to execute this Lambda function in near real time when whenever a user creates or modifies a security group. Which configuration will achieve this requirement? The choices are: Option A, subscribe the Lambda function directly to an AWS CloudTrail trail. Configure the Lambda to filter the CloudTrail stream for authorized security group ingress events. Option B, ensure an AWS CloudTrail trail is enabled and logging the relevant EC2 write management events. Create an Amazon Event Bridge rule on the default event bus that matches the security group creation and ingress rule modification API calls via CloudTrail, and set the Lambda function as the target. Option C, create an Amazon Event Bridge scheduled rule. Define a cron expression to invoke the Lambda function every 5 minutes to scan all security groups. Option D, configure an AWS config managed rule for VPCs open only to authorized ports. Set the remediation action to publish directly to the SNS topic. The right response is Option B. Ensure an AWS CloudTrail trail is enabled and logging the relevant EC2 write management events. Create an Amazon Event Bridge rule on the default event bus that matches the security group creation and ingress rule modification API calls via CloudTrail, and set the Lambda function as the target. This works because Event Bridge can match AWS API call via CloudTrail events on the default event bus and invoke the existing Lambda function. AWS documentation requires an active CloudTrail trail with logging for these CloudTrail-delivered Event Bridge events. Matching the EC2 security group write AP provides near real-time event-driven remediation without periodic account scans. Here's why the alternatives are not suitable. A. Lambda cannot subscribe directly to a CloudTrail trail as a live event stream. C. A 5-minute scan is polling, not near real-time event-driven remediation. D. AWS config can detect security group compliance, but this option does not invoke the already written Lambda, and only publishing SNS would not remove the prohibited rules. Here's a useful exam tip. For Event Bridge rules that match AWS API call via CloudTrail events, ensure a CloudTrail trail with logging is enabled, then match the right API calls on the default bus. Question number 31. A company is migrating from a self-hosted Jenkins CI server running on an Amazon EC2 instance. The DevOps team spends a significant amount of time patching the underlying operating system and maintaining the Jenkins plugins. Additionally, the security team now requires that all generated build artifacts, such as compiled JR files, be encrypted at rest before being deployed. Which solution addresses these concerns with the least operational overhead? Option A. Continue using Jenkins on EC2, but enable AWS Systems Manager Patch Manager to automate the OS updates. Attach an encrypted Amazon EBS volume to the EC2 instance to store the build artifacts. Option B. Migrate the CI workload to AWS Code Build. Configure Code Build to encrypt artifacts natively using an AWS Key Management Service, AWS KMS, key before storing them in an Amazon S3 artifact bucket. Option C. Migrate Jenkins to an Amazon Elastic Kubernetes Service, Amazon EKS, cluster to remove OS patching. Configure Jenkins to upload artifacts to an Amazon S3 bucket with default encryption enabled. Option D. Use AWS Code Pipeline to orchestrate the builds. Use AWS Lambda functions for the build stage and encrypt the resulting artifacts using AWS Secrets Manager before uploading to Amazon S3. Go with Option B. Migrate the CI workload to AWS Code Build. Configure Code Build to encrypt artifacts natively using an AWS Key Management Service, AWS KMS, key before storing them in an Amazon S3 artifact bucket. Let's look at the reasoning. AWS Code Build is a fully managed continuous integration service. Because it is serverless, it entirely eliminates the operational overhead of provisioning, patching, and maintaining operating systems and CI software plugins, unlike self-hosted Jenkins on EC2. Furthermore, Code Build natively integrates with AWS KMS and Amazon S3 to encrypt build artifacts at rest, easily fulfilling the security requirement without complex custom scripting. The remaining options can be eliminated because A. While Systems Manager automates patching, managing EC2 instances for Jenkins still requires maintaining the Jenkins application itself, managing instance scaling, and handling EBS volume lifecycle, resulting in higher operational overhead than a fully managed service. C. Migrating Jenkins to Amazon EKS removes OS patching but introduces the complexity of managing a Kubernetes cluster and containerized Jenkins controllers/agents. D. AWS Secrets Manager is used for storing secrets, like database credentials or API keys, not for encrypting large build artifacts. Artifacts should be encrypted via KMS and S3. Keep this point in mind for the exam. To minimize operational overhead for CI workloads, compiling code, running tests, packaging, replace self-managed Jenkins on EC2 with fully managed AWS code build. Here comes question number 32. Here's what is happening. A legacy application runs on a single Amazon EC2 instance. The application's durable state is stored outside the instance. During instance initialization, the application downloads its configuration files from an Amazon S3 bucket by using an EC2 user data script. The business requires the application to automatically recover if the underlying host hardware fails or the guest operating system becomes impaired. Because the configuration in S3 updates frequently, any replacement instance must execute the user data script to retrieve the latest configuration files. Which solution meets these requirements with the least administrative effort? Choice A. Create an Amazon Cloud Watch alarm monitoring the status check failed_system metric for the instance. Configure the alarm to trigger the EC2 recover action. Choice B. Create an Amazon EC2 auto-scaling group with a minimum and maximum capacity of 1. Configure the launch template to include the EC2 user data script that downloads the configuration from the S3 bucket. Choice C. Enable EC2 automatic recovery for the instance and create an AWS Systems Manager State Manager Association that periodically downloads the configuration from Amazon S3. Choice D. Create an Amazon Cloud Watch alarm monitoring the status check failed_instance metric. Set the alarm action to reboot the EC2 instance. Configure an event bridge rule to invoke an AWS Systems Manager run command to download the config after reboot. In this case, choose option B. Create an Amazon EC2 auto-scaling group with a minimum and maximum capacity of 1. Configure the launch template to include the EC2 user data script that downloads the configuration from the S3 bucket. This is the best choice because an auto-scaling group with minimum, maximum, and desired capacity of 1 replaces an unhealthy instance and launches the replacement from the launch template. The replacement runs the launch template user data at boot, so it retrieves the latest S3 configuration. This covers replacement after host or instance impairment without maintaining a custom recovery workflow. A. EC2 recovery is designed to recover the existing instance after supported system status failures and does not relaunch it from the launch template or rerun user data. C. EC2 automatic recovery plus a state manager association does not satisfy the requirement that a replacement launch execute the user data, and it does not provide the same replacement behavior for guest OS impairment. D. Rebooting on an instance status failure does not cover underlying host failure or create a fresh instance. The main takeaway is use EC2 recovery when preserving the same instance identity is required. Use auto-scaling replacement when recovery should launch a fresh instance and rerun launch template user data. Next up is question number 33. Next, let's move into IAM at scale. Here's what is happening. A company uses AWS IAM Identity Center to federate access for its development teams. Developers need to manage Amazon EC2 instances, but they should only be allowed to manage instances that belong to their specific department. All EC2 instances are properly tagged with a department key. IAM Identity Center is integrated with the corporate directory and is configured to pass the user's department as an attribute, which maps to AWS principal tag/department. Which IAM policy condition should the DevOps engineer add to the developer's permission set to enforce this attribute-based access control, ABAC? Here are the options. Option A, string equals EC2, resource tag/department, AWS, principal tag/department. Option B, string equals AWS, principal tag/department, EC2, resource tag/department. Option C, string equals AWS, resource tag/department, $AWS, principal tag/department. Option D, for all values, string equals AWS, tag keys, department. In this case, choose option C, string equals $AWS, resource tag / department, $AWS, principal tag / department. Here's why. Attribute-based access control, ABAC, in AWS allows you to grant permissions based on tags. When using IAM Identity Center, identity attributes from your directory, like department, are passed into the AWS session as principal tags, AWS, principal tag, to restrict a developer to only manage EC2 instances that share their exact department name. The IAM policy condition must check that the target resources tag, AWS, resource tag / department, matches the user's assigned principal tag, $AWS, principal tag / department. The syntax dynamically resolves the user's attribute value during the API call. Let's quickly check the incorrect choices. A. EC2. Resource tag is a valid condition key for EC2, but comparing it to the literal string AWS, principal tag / department, without the variable interpolation syntax evaluates to a static string comparison, which will fail. B. While the logic is somewhat inverted, comparing the principal tag to the resource tag string dynamically is less standard, but more importantly, it lacks the variable interpolation syntax on the right side of the condition. D. AWS tag keys checks whether a specific tag key exists on a resource or request, but it does not evaluate the value of the tag against the user's identity attribute. A helpful shortcut is this. In AWS ABAC policies, map the resource tag dynamically to the user's session tag using the condition AWS, resource tag / keyname, $AWS, principal tag / keyname. Remember the syntax is required to evaluate the principal's tag value dynamically. Next, question number 34. Scenario. A DevOps engineer is migrating a monolithic on-premises web application to AWS. The development team wants to deploy the application into a managed environment that natively supports blue/green deployments to ensure zero downtime updates and easy rollbacks. Additionally, the marketing team wants the ability to perform A/B testing by routing a specific percentage of production traffic to the new version before fully committing to the deployment. Which solution is the most operationally efficient way to meet these requirements? Options. Option A. Host the application on AWS Elastic Beanstalk. Deploy new application versions to a separate Elastic Beanstalk environment. Use Amazon Route 53 weighted routing to perform A/B testing between the two environment URLs, and use the swap environment URLs feature to finalize the blue/green deployment. Option B. Host the application on an Amazon EC2 auto-scaling group. Use AWS Code Deploy to perform an in-place deployment. Configure the Code Deploy deployment group to route 10% of traffic to the new instances using an application load balancer. Option C. Host the application using Amazon Lightsail. Store the application bundle in an Amazon S3 bucket. Use Lightsail deployment options to spin up a new container service and manage A/B testing through Lightsail DNS. Option D. Store the application code in AWS Code Artifact. Use AWS Code Deploy to deploy the application to a fleet of Amazon EC2 instances. Update the application load balancer listener rules manually to adjust traffic weights for A/B testing. The answer here is option A. Host the application on AWS Elastic Beanstalk. Deploy new application versions to a separate Elastic Beanstalk environment. Use Amazon Route 53 weighted routing to perform A/B testing between the two environment URLs, and use the swap environment URLs feature to finalize the blue/green deployment. The main reason is AWS Elastic Beanstalk is a managed service that simplifies deploying web applications. It natively supports blue/green deployments through the swap environment URLs feature, allowing you to seamlessly swap the names of a staging environment and a production environment with zero downtime. To perform A/B testing before fully swapping, you can use Amazon Route 53 weighted routing to distribute a specific percentage of traffic across the endpoint URLs of the two distinct Elastic Beanstalk environments. Now let's rule out the other options. B. Code Deploy supports blue/green deployments for EC2 instances behind an application load balancer. However, Code Deploy shifts traffic linearly or in a canary fashion for deployment safety. It does not natively provide long-term, percentage-based A/B testing logic for end users as seamlessly as Route 53 weighted routing across two persistent environments. C. Amazon Lightsail is designed for simple, small-scale workloads and does not provide native advanced deployment features like weighted DNS A/B testing or native blue/green managed name swapping out of the box. D. Code Artifact is a secure package repository like NPM or Maven, not a source code repository or hosting environment. Additionally, manually updating ALB listener rules is highly prone to human error and adds unnecessary operational overhead compared to Route 53. AWS Elastic Beanstalk natively supports blue/green deployments using the Swap Environment URLs feature. For A/B testing across two distinct environments, pair it with Amazon Route 53 weighted routing. Question number 35. This is marked as an easy question. A critical stateful application runs on a single Amazon EC2 instance. The application data is stored on an attached Amazon EBS volume. A DevOps engineer must ensure the instance automatically recovers in the event of an underlying hardware impairment, power failure, or network connectivity issue on the AWS host. To prevent data corruption and application disruption, the recovered instance must retain the exact same EBS volume, instance ID, and private IP address. Which solution will meet these requirements? Choice A. Add the instance to an Amazon EC2 auto-scaling group with the minimum, maximum, and desired capacity set to 1. Choice B. Create an Amazon CloudWatch alarm monitoring the status check failed_system metric for the instance. Configure the alarm to trigger the EC2 recover action. Choice C. Create an Amazon CloudWatch alarm monitoring the status check failed_instance metric for the instance. Configure the alarm to trigger the EC2 reboot action. Choice D. Add the instance to an EC2 auto-scaling group and configure an auto-scaling EC2_instance_ terminating lifecycle hook to detach the EBS volume before replacement. The best choice is option B. Create an Amazon CloudWatch alarm monitoring the status check failed_system metric for the instance. Configure the alarm to trigger the EC2 recover action. Amazon EC2 provides an automatic recovery feature triggered by CloudWatch alarms. The status check failed_system metric monitors for issues involving underlying AWS hardware, power, or network connectivity. If this check fails, the recover action migrates the instance to healthy hardware. Critically, a recovered instance is identical to the original. It retains the exact same instance ID, private IP addresses, elastic IP addresses, and all attached Amazon EBS volume data. The other choices do not work because A. Replacing an instance via an auto-scaling group creates a completely new instance with a new instance ID and new IP addresses. Furthermore, any data on the original EBS volumes, aside from the root volume AMI, would be lost unless complex lifecycle hooks and backup strategies are employed. C. Status check failed_instance detects OS-level issues, like exhausted memory or a crashed kernel, not underlying hardware or power failures. Rebooting does not migrate the instance away from degraded AWS hardware. D. While detaching the EBS volume via a lifecycle hook saves the data, attaching it to a new instance requires custom automation, resulting in higher administrative overhead and a new instance ID/IP address, violating the requirements. Exam tip. To recover an EC2 instance from an underlying hardware failure while keeping its instance ID, IP address, and EBS data perfectly intact, use a CloudWatch alarm on status check failed_system triggering the recover action. Question number 36. Let's go. An application runs on Amazon EC2 instances managed by an auto-scaling group. Upon boot, the application initialization script takes 10 minutes to download and process heavy reference datasets from Amazon S3 before it can bind to the correct port and serve traffic. During sudden traffic spikes, this 10-minute delay causes the application to become unresponsive before new instances are ready to absorb the load. A DevOps engineer needs to reduce the scale-out latency to under 1 minute while keeping compute costs as low as possible. Which solution is the most cost-effective way to achieve this? Choices. Option A. Configure an EC2 auto-scaling warm pool with instances held in the stopped state. Add a lifecycle hook for auto-scaling. EC2_instance_launching to allow the instances to download the S3 data before transitioning into the warm pool. Option B. Increase the desired capacity of the auto-scaling group permanently to handle the maximum expected peak traffic. Add an auto-scaling EC2_instance_launching lifecycle hook to track, when instances become healthy. Option C. Configure an EC2 auto-scaling warm pool with instances held in the running state. Modify the application initialization script to signal readiness to the auto-scaling group via the AWS CLI once the S3 download completes. Option D. Modify the auto-scaling group scaling policies to use predictive scaling. Configure an auto-scaling EC2_instance_launching lifecycle hook to place instances in the standby state while data downloads. The right response is Option A. Configure an EC2 auto-scaling warm pool with instances held in the stopped state. Add a lifecycle hook for auto-scaling. EC2_instance_launching to allow the instances to download the S3 data before transitioning into the warm pool. This works because an EC2 auto-scaling warm pool pre-initializes EC2 instances so they can be brought online rapidly during scale-out events. By configuring an auto-scaling EC2_instance_launching lifecycle hook, instances will boot, run their initialization scripts to download the heavy S3 datasets, and signal the hook to complete. The instances are then placed into the warm pool in a stopped state. When a traffic spike occurs, the pre-initialized instances are simply started, reducing scale-out latency to seconds. Keeping instances in the stopped state is highly cost-effective because you only pay for the EBS volume storage, not EC2 compute hours. Here's why the alternatives are not suitable. B. Increasing the desired capacity permanently forces the company to pay full EC2 compute prices 24/7 for instances that are only needed during spikes, which is not cost-effective. C. Holding warm pool instances in the running state means you are continuously paying full EC2 compute costs for idle instances, defeating the cost-effectiveness requirement. D. Predictive scaling can anticipate traffic patterns, but it does not fundamentally remove the 10-minute delay per instance, nor does placing instances in standby natively reduce costs compared to a stopped warm pool. Here's a useful exam tip. To reduce auto-scaling scale-out latency for instances with long initialization times while keeping costs low, use an EC2 auto-scaling warm pool configured with instances in the stopped state. Question number 37. A central operations team needs administrative access to multiple workload AWS accounts within an AWS organization. The company enforces strict separation of concerns. All IAM users for the operations team are created and managed centrally in a dedicated security ops account. No IAM users are allowed to be created in the workload accounts. A DevOps engineer must grant the operations team access to the workload accounts following AWS cross-account best practices. Which combination of steps is required? Choose 3. Identify all valid responses. Choices. Option A. Create an IAM role in each workload account and attach the administrator access manage policy. Option B. Configure the trust policy of the IAM roles in the workload accounts to allow the STS. Assume role action from the security ops account. Option C. Create an IAM user group in the security ops account and attach a policy allowing the STS. Assume role action targeting the IAM roles in the workload accounts. Add the operations team IAM users to this group. Option D. Create an IAM role in the security ops account and attach the administrator access manage policy. Modify the trust relationship to allow the workload accounts to assume it. Option E. Create an Amazon Cognito identity pool in the security ops account. Configure the workload accounts as identity providers to authenticate the operations team. Option F. Configure the trust policy of the IAM roles in the workload accounts to allow IAM pass role from the security ops account. The required selections are Option A. Create an IAM role in each workload account and attach the administrator access manage policy. Option B. Configure the trust policy of the IAM roles in the workload accounts to allow the STS. Assume role action from the security ops account. And Option C. Create an IAM user group in the security ops account and attach a policy allowing the STS. Assume role action targeting the IAM roles in the workload accounts. Add the operations team IAM users to this group. Let's look at the reasoning. This is the standard AWS architecture for cross-account access. The target accounts, workload accounts, must define what permissions are allowed. You do this by creating an IAM role in each workload account with the required administrator access permissions. A. The target roles must define who can assume them. You do this by configuring the trust policy on the workload IAM roles to trust the central security ops account, B. The source account, security ops, must explicitly grant its users permission to initiate the assumption. You do this by attaching an IAM policy to the operations team's IAM group, allowing the STS assume role action against the workload role ARNs, C. The remaining options can be eliminated because D. Modifying the trust relationship in the central account to allow workload accounts to assume it is backwards. The users are in the central account and need to reach into the workload accounts. E. Amazon Cognito is used for federating web and mobile application users via identity pools or user pools, not for managing internal IAM user cross-account CLI/console access. F. IAM. Pass role is used to pass a role to an AWS service, like granting an EC2 instance an instance profile, not for a human user assuming a cross-account role, STS. Assume role. Keep this point in mind for the exam. Cross-account human access requires 3 elements: an IAM role in the target account, a trust policy on that role allowing the source account, and an identity-based policy in the source account granting the user permission to call STS. Assume role. Now for question number 38. We're moving on to patch automation. Here's the scenario. A company manages a large fleet of Amazon Linux EC2 instances. Security compliance requires that all instances automatically install OS updates from the default Amazon Linux repositories. Additionally, the instances must automatically install proprietary application updates hosted in a custom corporate YUM repository. A DevOps engineer must fully automate this patching process across the fleet with minimal administrative overhead. How can the DevOps engineer accomplish this? Review the options. Option A. Use AWS Systems Manager Patch Manager to create a custom Amazon Linux patch baseline. In the patch sources, include the required default Amazon Linux repositories and the custom corporate YUM repository. Use a Systems Manager maintenance window to run AWS Run Patch Baseline on the fleet on a schedule. Option B. Use AWS Systems Manager to execute the AWS Amazon Linux default patch baseline document via run command. Use a pre-install script parameter to temporarily inject the custom repository into /etc/yum.repos.d/. Option C. Create an Amazon Event Bridge rule that triggers an AWS Lambda function on a schedule. Have the Lambda function connect via SSH to each instance. Execute YUM config manager to add the custom repository and run YUM update. Option D. Use AWS Systems Manager State Manager to run YUM update against the default repositories and use AWS Code Deploy separately to distribute proprietary packages from the corporate repository. Go with Option A. Use AWS Systems Manager Patch Manager to create a custom Amazon Linux patch baseline. In the patch sources, include the required default Amazon Linux repositories and the custom corporate YUM repository. Use a Systems Manager maintenance window to run AWS Run Patch Baseline on the fleet on a schedule. This is the best choice because for Linux, Patch Manager custom baselines can define alternative patch sources. When alternative sources are specified, only the repositories listed in the patch source configuration are used, so the required default Amazon Linux repositories and the corporate YUM repository must both be included. A maintenance window running AWS Run Patch Baseline provides centralized scheduled patching across the fleet. B. The default patch baseline is not a run command document, and temporarily injecting a repository is unnecessary custom handling. C. A scheduled Lambda function that connects to instances over SSH adds credentials, network dependencies, and custom code. D. Splitting OS patching across State Manager and proprietary package deployment across Code Deploy creates extra operational mechanisms when Patch Manager can centrally manage the repositories. The main takeaway is with Patch Manager alternative Linux repositories, explicitly list every repository needed for the patch run, including required default OS repositories, and schedule WS Run Patch Baseline centrally. Here comes question number 39. Consider this situation. A company uses an AWS Storage Gateway file gateway deployed in their on-premises data center to provide local SMB access to an Amazon S3 bucket. An external partner application uploads new data files directly into the S3 bucket every night. However, when on-premises employees arrive in the morning, they report that the new files are not visible on the file gateway's mounted file system. When a DevOps engineer inspects the S3 bucket via the AWS console, the files are present. Which solution ensures that the updated files are automatically available to on-premises users every morning? The choices are: Choice A, create an Amazon Event Bridge rule that triggers on a schedule every morning before business hours. Configure the rule to invoke an AWS Lambda function that calls the Storage Gateway Refresh Cache API. Choice B, instruct the external partner to upload the data into the S3 bucket using AWS Transfer Family instead of the direct S3 API to automatically invalidate the gateway cache. Choice C, modify the storage gateway configuration to run in volume gateway stored mode to force continuous synchronization of block data from S3. Choice D, configure S3 event notifications on the bucket to trigger an AWS data sync task to push the new objects directly to the on-premises file server. The right response is option A. Create an Amazon Event Bridge rule that triggers on a schedule every morning before business hours. Configure the rule to invoke an AWS Lambda function that calls the Storage Gateway Refresh Cache API. Here's why. An AWS Storage Gateway file gateway caches the directory listing and metadata of the associated Amazon S3 bucket. If objects are added or modified directly in the S3 bucket using native S3 APIs, like the external partner application, the file gateway is unaware of the changes. To force the gateway to discover the new files, you must invoke the Refresh Cache API. Automating this via Event Bridge and Lambda ensures the on-premises cache is synchronized before users arrive in the morning. Let's quickly check the incorrect choices. B. Uploading data via AWS Transfer Family interacts directly with S3 APIs, which does not notify or invalidate a remote storage gateway cache automatically. C. Modifying the gateway to volume gateway stored mode changes the entire architecture from file level SMB/NFS to block level ISCSI, which breaks the current S3 object integration. D. AWS data sync is for large-scale data transfers, not for invalidating the cache of a storage gateway. Furthermore, S3 event notifications triggering data sync to an on-premises server bypasses the storage gateway entirely. A helpful shortcut is this. If files are uploaded directly to an S3 bucket backing a storage gateway file gateway, the gateway will not see them until the cache is refreshed. Automate the Refresh Cache API call using Event Bridge and Lambda. You have completed Set 2 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.